So I started to grade the Excel worksheets, but I didn't quite finish yet. So I should finish today. Any let's see, any other questions? Yes.
So on the syllabus, the point breakdown for the class.
Yeah.
So like, where is the attendance?
No, I have to report attendance, but it's not part of the grade. Other questions? Okay. Okay. So let's see. So today we want to keep going, right? We started probability last time, and we want to learn about more about Venn diagrams, and we want to apply contingency tables. Okay, so we'll see what those are about. And then we also want to start with the introduction to conditional probability. And the main reason why we want to do that is we want to get to this concept of independence, which we'll get to probably next time. Okay? So last time we started to think about random experiments, and what they are, right, is it's a process whose outcome or result is not known with certainty. And we talked about events or simple events. And then we talked about the sample space, which is the collection of all of the events that are possible. And oftentimes it's abbreviated with some type of an S, and then the null set or an empty set. And then we talked about a random variable, which is a way to assign a numerical value, right? So, and then we abbreviated it with a lowercase. So capital RV would be this like RV, recreational vehicle kind of thing. So I don't think we'll get confused, but we'll stick with a lowercase random variable, right? Okay, so then after we thought about the events and the sample space and so forth, then we actually started to talk about probabilities, and so that's when we want to start assigning probabilities. Okay, and what is a probability, right? It's really a fraction or some kind of a decimal that expresses how likely an event is to occur. And so when we have these events, right, we have this random experiment, and then there are possible outcomes or results of the random experiment. And so we assign probabilities to these results. We assign probabilities to these events, to these outcomes. And we just basically, at least with discrete probability, we count up the number of times this event happens, and we divide it by the number of possibilities in the sample space, and then that fraction is the probability. Okay, and there's a few ways to assign probabilities. Empirically is we actually conduct an experiment. So after you conduct the experiment, then you know what the probabilities are, or you can estimate the probabilities. Classically, if you study the components, you may be able to assign probabilities a priori or ahead of time before you even begin. Sometimes you cannot do either one, and you just kind of make a guess, make an estimate. Okay, and so probabilities again are between, it can be 0 as a lower bound, and they can be 1 as the higher bound. And there's this null set. The probability of the null set is 0, and the probability of the entire sample space is 1. Okay, so then we looked at some basic concepts. One would be the complement, which some books use signal or use a notate with a bar above the set, and others notate with this little asterisk or apostrophe or prime. Sometimes they call E prime, like this little 1 dot over there. And what it is it's the opposite. So everything that's not in. So sometimes people will say not E, or E bar, E prime. Okay, and that means the complement of the set E, the complement of the event E. And then we started to look at ways to, say, combine probabilities, right? if we union or do an or kind of an operation, and then we have an intersection. Okay, so right. So let's take a look. And so we started to think about, this general law of addition, where the union is or, right? And so when you combine probabilities this way, you're adding them, right? And so you get a bigger probability. Okay, right? So you're say you want to know what's the probability of either E or what's the probability of E or F happening. So you start out with the probability of E, right? Clearly, if you're looking at the probability of E or F, right? Probability of E could be a baseline, and then you're going to add more probability to it. So the probability will get larger. Okay. So the problem is, right, you have to be a little bit careful, right? Because if you add the whole entire probability of E and then you add the entire probability of F, then there's this intersection that's actually added twice. Okay, and so if you have that, then in order to get the correct amount, you have to subtract one of the intersections, right? Because when you added E, you got one copy of the intersection. And then when you added all of F, you also added a second copy of that, or probability measurement. And then you have to subtract one of them. Okay, leave one in there and take out one. And then you've got it. Okay? And there's kind of a special case where if the intersection is empty, we call that mutually exclusive. So E and F are basically have no overlap, have no intersection, and then you can straight add. Okay, because you could say, well, if there's no intersection, the probability of an intersection, and E and F happening at the same time is 0. There's no way that they can both happen at the same time. Then we can just do a straight add. Okay, add them without this bothering with this correction. Okay. And so we looked at a Venn diagram, right? So the Venn diagram is kind of nice to look at the sets, right? It's a little bit, confusing about the stuff that's not in the sets. But what is really, really nice about the Venn diagram is it clearly shows you, here's one, here's the other one, here's the intersection. And then, maybe there's this stuff outside, and you might almost forget about this stuff outside, right? But if you want to look at E, E was the even number, so 2, 4, 6. F was, 4 or greater, right? 4, 5, or 6, right? So clearly there's this intersection here, but F is 4, 5, and 6, and E is 2, 3, 4. And then you might say, oh yeah, what's not in E and not in F? So this is, not in E and not in F, right? The complement is the stuff that's not in E and not in F, right? So it turns out that there's another useful way to help you visualize or handle or deal with probabilities, and that's a contingency table. Okay, so this is what a contingency table is. The contingency table basically it's the same view as the Venn diagram, but it's like a table, tabular. It's like a table. Okay, and so in this column there's all of E. Okay, and then in this column there's all of that's not in E. Okay, and then sort of in this row there's all of F, and then in this row there's what's not in F. Okay, so in a certain sense, this entire table, this entire box, is like this whole frame, the total sample set, the total of everything in the Venn diagram is kind of like this whole frame. And what's in E over here, right, that's like this part over here, right? And so you can see that in the Venn diagram there's a circle, so there's the intersection part, and there's a part of E that's not in F, so it is in E, but it's not in F, right? So that's why it's in E, but it's not in the intersection, right? So the intersection is right here, the E and F, so here's where E and F intersect. and then continuing with E, right? So here's the part of E that's not in F. So what's not in F is outside of F, but it's still in E. So that's why this, in this case, this column in the contingency table is like the circle or this ellipse in the Venn diagram, right? Similarly for F, which is this row, it's kind of like this circle or elliptical closed set here, right? Where again, F has the intersection, right? So F has, so E was looking at this way, F is looking at this way, but clearly the intersection is also in F. And then here's the part of it is in F, the other part of F that's not in E. So this is what's in F and not in E. So that's this part. Oh, maybe there should be, oh yeah, E, right? Yeah. Okay. Not enough. It's just flipped around. Okay. And then, of course, the part that's outside, the part that's not in E, right? Not in E, and the part that's not in F is more clearly visible because it's kind of has its own level, right? Here, it's kind of you're kind of like focused on the set and the intersection. It's really strong on that area, but then the stuff that's not in E and not in F, it's kind of like, well, it could be, you know, anywhere in this whole region. Whereas in the table, it has its own box. Okay, so here is E, right? 2, 4, 6, the evens. Here's F, and so also in the table there are these marginal stuff. The margins actually contain a lot of information, like a lot of information. And so the trick with dealing with the contingency table is, you know, you set it up in the middle, and then to really understand this outside stuff, this margin stuff outside of the contingency table. Okay, so here's E. So this would be E, and so at the bottom of margin we sort of have some description of E, and then here's F on this row, and so on the margin for F, outside margin of F, we have 4, 5, 6. So if we wanted to make this table for E, what should we do? How should we do that? Where do you start? Start where? You start in the top left corner. The top left corner is the intersection, right? Because it's kind of like, how do you know? So you want to have what's in E, right? You kind of want to have what's in F, right? But how do you know what goes out in here, right? So you should start with the intersection, right? When you want to draw the Venn diagram, you start with the intersection. You should figure out what the intersection is. And when you want to fill in the contingency table, you should start in the top left corner. Right, you should start in the intersection. So what's the intersection between 2, 4, 6 and 4, 5, 6, right? So you can see the intersection would be 4 and 6, right? The intersection is 4 and 6. So you should say 4, comma 6 over there, right? And then to finish up E, right? Oh, sorry. No. Go away. Okay. To finish up E, we have the 2. Okay, and so what that's saying is this is, right, E, right? So this cell or this part of the table is E and not an F, right? So that's an E and it's not an F. Okay. So then we got E. Now we have F, right? And so for F we already, so now we're kind of like doing this part, right? So already have the intersection, and this 5 is in F but not in E, or and not in E, right? So that will be 5. Okay, so then, you know, if you're doing the Venn diagram, you might just concentrate on this stuff and say, okay, I got it, I'm done. And then you might say, oh, I forgot about the stuff that's outside, you know, of the 2 sets, but inside the, still in the universe or still in the sample space. Here, if you have the contingency table, there's still that puka, right? There's still this one opening over here that's empty. And so then you could say, well, what do I have left, right? 1 and 3, right? 1 and 3. Okay, so that's basically how the contingency table and the Venn diagram really show the same information, but it's obviously presented differently. Okay? So, so here's our contingency table, right? How do we use the contingency table to compute probabilities? Right, so what's the probability of E? We already kind of know the answer, right? It's a half, right? Because there's 3 there and there's only 6 elements. So we know, we can just sort of look at it and know that it's a half. But it's actually good to do it step by step, because then, you may come across a situation where you cannot just spot the probability, and then you have to use the method, the analytical approach, the process of going through the steps to figure out what the to compute the probability. So even though we already know the answer, it's worth it to go through the steps so that when we encounter those other cases, we know what to do to get the probability. So how do you get a probability? How do we compute a probability? What is a probability? Sorry? The probability is the likelihood of something occurring, right? So how do we compute it? So suppose, how do we compute a probability? How do you get it? Right. So it's the likelihood of something occurring, right? It's a fraction, and so there's a numerator and a denominator, right? So you gotta, to do the fraction, you have to compute the numerator, and then you have to compute the denominator. And so, in the numerator, we have the number in E, the set of interest. So we copy this one over, right? So what you want to find the probability of, that goes in the numerator. And then what's the denominator? Right, the likelihood of something occurring, it's out of the whole thing, right? So, and the whole thing is the sample space, thanks. So in this case, we could just say S, perhaps. In this case, we know it's 6, so whether you put 6 or leave it out, that's kind of like splitting hairs, right? But at least S, right? That's everything, right? And so we know in this case how big is the sample space. We know that it's 6, right? And so then for the evens, the number of evens, 2, 4, 6, there's 3 of them, right? And then when you simplify that, you get a half or 0.5. Your choice, right? And so probability of F, right? That's basically the whole thing, or the same thing. Probability of F and the probability of the sample space. Here I'll just say S instead of S6. And so again, say 6 in the denominator, and then the likelihood of F occurring. Well, how many cases are there? Well, there's same as 3, so it's a half, or this same 0.5. Okay. So how about the probability of E or F? Right? I mean, one way to do it, say directly, is to say E union F over S6, say. And so we could count, right? 1, 2, 3, 4. Okay? So there are 4 out of 6, and so it's 2/3, which is, we'll just call it 0.67, say. or 6, 6, 6, 7, because the 6 will repeat on and on forever. Right? But there's another way, right? We know that it's this union, which is OR, and so we could say do the probability of E plus the probability of F. But if we do that, what do we have to do? We have to subtract the probability of the intersection, right? E intersect F. Right, so here we know that this is a half plus this is a half. And the intersection is actually 2 over 6, say. So actually, maybe it's better to do this, right? Because if we do this, then we can plug in the number, right? So the intersection has clearly the number in E intersect F, right, over the number in the population or the sample space. That's 6, so that's equal to 1/3, right? So we know that we want it to be in sixths, so we'll put in actually, why don't we just put in 1/3? So clearly this is 1, a half plus a half is 1. So 1 minus a third is 2/3, or 0.67. Okay, so here we were able, because we can just inspect and count the intersection. We can count the number of elements in that set, and then we can compute it directly. Also, we know the general rule for additions, and so we can apply that and we get the same answer. Does that make sense? Good? Okay. So what we want to take note of, right, is that when you have OR, right, you're adding, and what you do is you get a probability that's bigger, right, because the probability of E by itself is a half, the probability of F by itself is a half, and if you want E or F, you include E, you include F, and so you add them. You're adding basically the probability of E and you're adding the probability of F, and so you're getting something bigger. And then of course, if they're mutually exclusive, you have to have this little correction, but basically you're adding, OR is adding probabilities and the probability is getting bigger. Okay. Meanwhile, if we do AND, it gets smaller, right? Because now we're looking at a part of E, right? Like that part of E. Right, here's E, so we're looking at that part of E, and we want that part of F, like that part of F, right? And so here it's a third, which is obviously 0.33, say, and so the original probabilities were a half, probably E, probably of F were a half, 0.5, right? And so now the intersection is smaller, right? Because it's a little bit the part where they overlap. Okay, so it's smaller. Okay, and so actually, what we'll see very soon is that and so add. What other operations there? Multiply, perhaps. I mean, there's subtract, right? But multiply. What happens if you take a fraction and you multiply it by a fraction, like a half times a half? You get a quarter, right? You multiply two fractions together and you get a smaller number. Okay, and so what we'll see is that when you do AND, you're actually multiplying probabilities. Okay, that's what we want to. One of the concepts we want sort of to sink in today is that this intersection, this AND, is multiplying probabilities. Okay, so when you add them, you get a bigger result, and when you multiply them, if you multiply two fractions, you multiply two probabilities, two fractions together, you get something that's smaller, and that kind of is on the right track. Okay? So let's do an example, though, a quick example. So for a class, students conducted a survey of 100 people. 60 people were under 40, and 20 of them used Mac. The remaining 40 people, right, 100 people, of the remaining people, remaining 40 people, only 10 used Mac OS. Okay, So suppose that we use this survey to estimate the probabilities for the general population. You know, what method of determining probabilities is this? What were the methods for determining probability? Right, classical. Thank you. Subjective or empirical. So, which method is this? Conduct a survey. Well, careful, because classical means that you're looking at the die, say, and you know the die has 6 sides, and you assume it's a fair die, and so you say each one is 1/6. So you know that, suppose that you want to know what fraction of people use Mac, and does age make a difference in people in so classical would be, I reason, this way. Subjective would be, well, I think that it might be whatever. So when you do the survey, are you saying, I think it might be this? What does empirical mean? Right, empirical means that you gather results. It's something to do with results, right? Right, gather results. So in other words, in order to gather results, what do you have to do? You have to do something, right? In order, you get results. Results mean that you did something and then you gather the results, right? So empirical has either to do with like an experiment or possibly a survey, right? You get out there and you collect the data, right? So what method is this? This is actually empirical, right? Because, why? Because of survey, exactly. Because it's a survey. Okay, so this is, and so before you conduct the survey, do you really know? Well, you might guess, you might have an idea, but after you conduct the experiment, a posteriori, afterwards, you have the data and then you know. So this is sometimes people will use contingency tables to find probabilities. You do an experiment and then you find probabilities afterwards. Okay? So suppose that we pick someone from the survey. Suppose we pick someone from the survey. How likely is this person to be under 40 and not use MacOS? Oh, sorry, I think this one may be actually the same thing as A. So there's a lot of numbers flying around, right? 100 people, 40, 60, 20 this, the remaining 10, right? There's all of these numbers kind of floating around. When there's like a lot of numbers like floating around, what do you have to do? You should work it out, like organize them, right? So lots of numbers. So you need some help. And so what you should do is you should think about organizing. So how could you organize all of these numbers? What's a way to keep numbers, sort numbers out? Make some kind of a chart, right? Chart, table. so what kind of a chart or table should we try to set up? We could set up a Venn diagram. Right, and so the Venn diagram would look something like this. So how do we figure out the Venn diagram? Actually, let me tweak that a tiny bit, and we'll say, something like that, right? So we need to know, what's that? And we need to know what's that, right? So the Venn diagram has like two sets, at least two sets, right? You could have 3, 4, of course, if you have three or four, right, it's going to get a little bit messy having the, what's in the intersection, because, but anyway, in this case, we'll just stick with 2, right? So what should, one circle be, and what should the other circle be? One should be under 40. So let's see. This one is a little bit longer, and this one's a little bit shorter. So we'll just say under. Oops. Let's see. Under 40. Okay, under 40. And then what should the other one be? Well, if one is under 40, then the sort of complement of that would be what? Under 40 complement is the same as over 40. Does that make sense? Because when we think about what's in under 40, we kind of automatically get what's outside of under 40. We kind of get what's over. So if we pick one of the categories, we get the other one. See, it's kind of like, this, where if you pick an E and you put things in E, then you get the stuff that's not in E is outside of it. Yeah, kind of. So by picking one of these, this is why we're going through the exercise, right? So when you pick a category, you don't have to have, you shouldn't use its opposite, because you can say the complement to get the other half, the other part of the sample space. So we got 1. What's the other one? Mac, right? MacOS. Okay, so here's our universe. And how big is our universe? Our universe is 100, right? Because they surveyed, or not universe, but sample space is 100. So our box, big box in the Venn diagram is 100. Oh, maybe I should continue. Okay, so when you want to sort of fill things in, how do you fill things in? So 60 people were under 40. So how many people do we have to have in the under 40 circle? 60, right? So we'll just sort of put 60 on that boundary, right? And so, right, okay.
Where? 20 inside where? Inside where?
For math.
So where would we put the 20?
Oh, wait, did we not? Oh, we didn't designate a spot for it yet. Yeah. In the middle, right?
In the middle? Where? What's the middle called? You mean like right there? So we should put 20 over there. Is that right? Why should we put 20 over there? Because of these 60, right? 60 people were on. So this this is our. So maybe we should say we'll say B, right, equals under 40, right, and then we'll say A is MACOS. So, right, so 60 people were under 40. So here we have this B under 40. There's 60 people. And of those, 20 use MACOS, right? So that's the intersection. So what goes over here? Right? 40, because the total set of under 40, there's too many numbers, right? Under 40 is 60. And so 20 of them also use Mac, and so 20 of them don't use Mac, right? They use either possibly Linux or possibly Windows, right? But all we know is they just don't use Mac. Okay, so of the remaining 40 people, only 10 used Mac. So how do we do that? So we could put I messed up. How should we do this? So somehow MACOS, we have to have so of these remaining people, right? Some use Mac. 10, maybe. 10 use Mac. And then there are 30. Sorry. Of the remaining 10 use Mac, and then there are some 30 outside. Does that make sense? Because then here, this is Mac. Oh, sorry, this is under 40, and we know that under 40 has 60 people. Right? And so our other set is the number that use MACOS. Right? So here we have, so outside of under 40, we have some that use Mac and some that don't use Mac. Does that make sense? Yeah? So how likely is a person to be under 40 and not use MACOS? So under 40, right? So that would be, say, B, right? Because B is under 40, and not use MACOS. And so that would be A not and. So we want the intersection. So it's got to be in B and not in A. So in B, but so B has two parts, right? There's a part of B that's intersects with A, and there's a part of B that doesn't intersect with A, right? So it's 40, right? So A, oops, A, I guess I should say A is A intersect, not A intersect B, and so that will be 40 over 100, or 2/5. Does that make sense? So how likely is the person to use MACOS? Sorry? B, right? So that's basically the A, right? How likely is a person to use MACOS? And so that's all of A. So we want the part of A that intersects with B, and we want the part of A that does not intersect with B, right? So that's equal to this 10 plus 20, oh, sorry, equals 30, right? So that's 30 over 100, which is 3/10. And C?
Oh wait, how do you know how like you did the top for A, you wrote like complement A, minus the other one, and how do you write out for B? Just wrote A as well.
So what's A? Sorry? A is the people who use MACOS. Does that make sense? So it's a little bit tricky. So sometimes we're looking at these compound things, right? And sometimes we're looking at the total set by itself. Okay, so good question. We want, so how likely is the person to use MACOS period or question mark, end, stop. It's not how likely is the person to use MACOS and be under 40 or and be over 40, right? It doesn't continue and, or, right? It just stops. And so that's the trigger to that you want the entire set, not, that one and the union with another one, this or that, or not this and that, right? But you just want itself. Yeah? So that's why you take the whole circle. Okay? And then next one, C. What is the probability of a person to be over 40 and use MACOS? Right, so it's and. So what should we use? We need to have and you should think of meaning we need if it were or, what would we use? If it were or, we would use union, right? So and we use intersect, right? So there's and, so we're going to have some type of intersection. Probability of a person to be over 40. So if B is under 40, then over 40 is the complement of B. So it doesn't matter if we could put it on this side or we could put it on the other side. If we keep A on the left, and B on the right, it doesn't matter which was left or right. But if we have a convention, we put A on the left and B on the right, right? So C, what is the probability of a person to be over 40? So if B is under 40, then the complement of B is over 40. Okay, so we'll put the complement of B, and then and use Mac-Os. That's straight A by itself, not A complement. So what's that? We want A, so it's got to be A, and not B. So the part of B, that part of B is out, right? So we want 10. So that's 10 over 100, which is equal to 1/10, which is equal to 10%. Does that make sense? So what's another way to do this? So to sort of recap a little bit. Recap. What was really the first thing that you should do? The first, how did we really? I mean, it's kind of like we're a little bit confused, right? And so we want to do problem solving, right? So how do you solve this problem, right? When did we start to be able to make progress? We started to think about the Venn diagram. Some type of a framework or tool. In this case, we thought of the Venn diagram. Sort of like the things that we learn in class are supposed to help us, right? Okay, so yes, we just learned about that, and so it helped us. So it's a way of organizing, right? Way of organizing. Okay, so what kind of a problem is this? Is this a cost volume profit? No. Is this a time value of money? Well, no. So what else? It's a probability problem. Okay, so it's about these probabilities. This and that. By itself, and the Venn diagram has a lot of these little and category things. Yeah. So what framework? FR, right? Framework. What method are you going to use? So then what? So you start to use it. So you think about the Venn diagram, right? So I kind of made a scratch Venn diagram over here, right? Okay, I want to use it. Okay, well, how do you use it? So what's the next step that you have to go through? The Venn diagram is basically it's a story about what? Two different what? Two different events, right? So Venn diagram is a story about two different events, right? It's a story about two different events. So if you're going to use the Venn diagram, what do you need to identify? You need to identify the two events, right? Must ID identify the two, or more. We'll just stick with two, right? Two or more events.
Okay. Basically, what are the events? Okay. So good. Use a Venn diagram. Okay. How do we use a Venn diagram? It's a story about events. It's all about, intersection of this one and that one, intersection of this one and a complement, this and that, right? And so what are the events? And then, just recall, sort of E and E complement. So do not need a separate event for complement. Okay, you don't, you once you identify the one set, you can get the complement kind of for free. Okay, so you don't need a separate set for the complement. Okay? And then when you start to do the Venn diagram, where start Venn diagram? So we know we want to use a Venn diagram. We define our events. Where do you get started? In the you kind of start in the middle. Is that right? So find the intersection. Start with intersection. Okay. Is there another way that we could have proceeded? Who's the Venn diagram's cousin? The Venn diagram's cousin is the contingency table. The Venn diagram, so whenever you could use the Venn diagram, you could also use the contingency table. Okay, could also use contingency table. Okay. They're actually cousins, right? Oh, rats. Maybe I'll just say they're related. Okay, so we would have either way, say A, not A, B, not B, right? And so basically we would have 20 in there. The rest of A looks like it will be, so B, you say you would have 60 out there. And then A, I guess, not A would be, the remaining would be 40, right, for the, they're 40, right? And then we know that B, so this is B, so B is this way, right? So B would be 40 over here, yeah. And then we got A and not B would be 10, and then 30. What would be this outside one would be this 30. Okay, so then we go 30 and 70, and then the whole thing should add up to be 100. So whether you add it up this way or you add it up this way, this bottom corner one should be the same, right? So if this is 30, that's 40, this is 60, and that's 40, so yeah, okay? So then it works out. Okay? So, whether you think of the Venn diagram or the contingency table, there's just so many numbers, right? And it's in this one, it's not in that set, in the two different sets, that it really helps to have some type of a framework or tool to help you organize and sort through the information to figure out what is going on. Does that make sense? Yeah? Okay. Okay. There's another sort of technique, which is sometimes I think of it as working smarter, not harder, right? Where you kind of use the complement. Okay. So here's an example, right? You need to get a signature from one of two administrators. So you could do one or the other one of them. Okay. Because the first administrator participates in so many meetings, the probability of finding her available is 30%. Okay. The probability of finding the other administrator available is 80%. Okay. The combined probability of finding them both available is 25%. What's the probability that neither is available? So how would you do this one? The intersection. So add up guess what, probabilities, and subtract intersection. Right? So maybe you're thinking about something. Does anyone remember what that's called? The general rule for addition. Right? So clearly, right, it's about events. Right? So as you start to work with these, the question is, right, what are my events? Right? So you can really kind of use anything that you want, but here we'll just say A1 is sort of busy administrator is available. Okay. The second administrator, I'll just use is available. So A1 is that the busy administrator is available, and A2 is that the other, or the second administrator, is available. And so here, right, you need to get a signature for one of two administrators. What is this about? You could get a signature from one, the other one. So this problem is really about what? One administrator, the other one. This problem is really about OR, right? And when you see OR, you think of what? Right? Union? Is that right? And so that's, the general rule for addition is about union. Okay, so whenever you see union, or as a check, I'm thinking of using the general rule for addition, that's about OR. So is this problem about OR? And it is, right? Because you get a signature from this one or the other one, right? So basically, what are we looking at? We're looking at P, the probability of A1 union A2, right? So we want probability of A1 plus the probability of A2 minus the probability of A1 intersect A2, right?
probability of A1 is 0.3. Probability of finding the other one available is 0.8. And the probability of finding them both available is 0.25. 0.25. Right? So actually we have 1.1 minus 0.25, right? So that's 5. So then that's 8, right? So that's equal to 0.85. Does that make sense? And so here, this is just a quick calculation of odds, right? What are odds? You know, if the probability is of 1/3, you take 1/3 and then you just divide it by the complement, which is 2/3, and so this gives you 1 to 2. Probability against that would be 2/3 over 1/3, and so that basically gives you 2 to 1 odds. So sometimes they say 1 to 2 odds, and this would be 2 to 1 odds. Okay, but anyway, I don't want to spend too much time on that. On the other hand, we want to think about you know, a multiple choice question with, say, 5 choices. Okay, so what's the probability that answer choice A is correct? 20%, right? Right, and so how do you get that, right? So you really want the probability of A, right? So that's, you know, how many choices are in A over how many choices are there in total. So A is 1 choice, there are 5 choices, 1/5 is 20%. Okay. So suppose that you gain some additional information. Suppose now you know that choices D and E are not correct. Choices D and E are not correct. What's the probability that choice A is correct if you now know that choices D and E are not correct? Sorry? 1/3, right? So we know that it's 1/3. So basically, now, let's say you want the probability of A given, and so let's say that given that D, given that it's not D and not E. So let's just say that, you know, A means A is correct, and so not A means not correct, and so we'll follow that. So our problem has changed, right? So here it's like, what's the probability of A? 1/5. Now we have probability of A given, so this vertical bar means given, that D is not correct and E is not correct, and we know that actually, and we know that it's 1/3. So how do we get that sort of more analytically, right? So what we want to do, right, is so what has happened, right? This is our numerator. Our denominator. So here, obviously, this is the numerator, right? And this is the denominator. Okay? So when we got the new information, what changed? Our sample space, right? So new information changed sample space. Okay? So basically the formula is the probability of A given, whatever, is the probability of A intersect DE divided by the probability of that. So you basically take this one and this one, right? And you AND them. So if you see, given that, you take their intersection, and then whatever it's given by, you divide by that one.
So like, where you have the answer though, right? Or just like how to show it. That's just how to show it.
This is how to show it.
Okay.
Because it's easy to see that it's 1/3 here, but the question is, what happens when you come up with other conditional? So this is called, when you have this additional information, this is called conditional probability. Okay. Sorry? 4 types of probability? What do you mean? Oh, no, it's not one of those. There's still only 3, empirical, subjective, that's how you define probability. This is another property of probability. Okay, because we're still working with probabilities that we have. Okay? So, believe it or not, what's kind of helpful this is a contingency table. And so what we'd like to do is we'd like to understand the probability that A is correct and the probability that not A is correct. The probability that A is not correct, right? And we want to compare this to not DE and let's say because we want this to be here, let's look at the probability that D and E are not correct. And then here it's the probability that D and E are correct. Okay, so what's the probability that A is correct and D and E are not correct? So let's say that it's if A is correct, then B is incorrect, C, D, and E. Right. So now the lowercase means that they're not correct. Okay. So meanwhile, right? If A is not correct, right, and D is not correct, then we could have A, B, C, D, E, or A, B, C, D, E. Does that make sense? So here we have the case where A is not correct, and D and E are not correct either. So that means that either B is correct or C is correct, right? And here, this one is A is correct and D is correct and E is correct, so that never happens. Okay. Now, in this case, it's that D and E are correct and A is not correct. So A is not correct, so B is not correct, C is not correct either, and so D is correct and E is not correct. Or we have the case where it's A, B, C, D, or E is correct. Right? And so now we have all 5 of them, right? So here's 1, 2, so A is correct, all the others are wrong. B is correct, all the others are wrong. C is correct, all the others are wrong. D is correct, all the others are wrong. And E is correct, all the others are wrong. Does that make sense? Okay, so let's check this formula. A and DE would be this intersection, right? So it's actually 1 out of 5, right? And what we want to divide by is this DE. So what's the probability of this DE? There's 3 of them in not D, right? If D is not correct and E is not correct, right, then either A is correct, B is correct, or C is correct, right? And so if A is correct, B is correct, C is correct, that's actually 3 out of 5. Does that make sense? Does that make sense? So it looks a little weird by having a probability and you divide it by another probability. But look what happens, right? Becomes 1 over 5. And then to do the division, we take the reciprocal, 5 over 3. Right? So what has happened when we do this? This is out with the old sample space and what? In with the new sample space. Does that make sense? So this story is out with old S, in with new S. Maybe just I'll write it as a script S for the new sample space. Does that make sense? And so that's why, I mean, when you first look at this, it's like, oh no, it's a probability divided by another probability. Oh, right? It's like, what is that? Okay, but if you actually look at it, this is the probability that's kind of going away. So what's the probability of this happening? So you're conditioned on this. So this did not happen. And so we want to get rid of it. So what's the probability of that happening? The probability that D or E is not correct, well, that means that A is correct, B is correct, or C is correct. So that's 3. So that's 3 out of 5. Okay? And then when you actually do that division, right? And so what happens if you take a number and you divide by a fraction? Right? Gets bigger. Right? You take a number and you divide by a number larger than 1, like you take, divide by 5. You get smaller, right? So if you have a number and you divide by, something bigger than 1, you get a smaller number, right? Divide by 10, it's smaller. If you divide by a fraction, it gets bigger. Okay? So you take any number, you divide it by a fraction, and it gets bigger. So that's what we're doing. We're taking this probability, we're dividing by another probability that's smaller, and we get something that's bigger. Does that make sense? Okay, and so really what it's doing is it's out with the old sample space and in with the new one because the new information has changed the sample space. Does that make sense? Okay, so here we go, next page. This is the formula for the conditional probability. Okay? Does that make sense? So I know it's like a little bit hairy, a little bit tough. Really, why are we why are we doing this? What we're doing this is because we want to get to this stage, and we want to see that. Remember, kind of we mentioned if you have a union, it's OR, so you're adding probabilities together. Here, when you have intersection, you're multiplying probabilities. So it's kind of we're getting at this backwards. So this is the formula that we just talked about. But if it's just math, you just multiply by this probability of f, and now you see that intersection is multiplication. Okay, so don't get so hung up on just remember that when this is called conditional probability. When you have additional information, sometimes it changes the probability, sometimes it changes the probabilities. And we want this formula because it has the intersection involved. And what we really need going forward is that when you have a union, you add. When you have an intersection, you multiply. And the last piece of the puzzle that we need before we can move on is something about independent events that we'll talk about tomorrow. Okay, and it's related to this conditional stuff. Once we have independence, then we can move on to the next topic. So don't get so stuck on the details, but just remember that you're dividing by this probability, and that makes it larger. Because 1/3 as opposed to 1/5, right? Okay, so see you tomorrow.